So this section is about two things. One, modeling quadratics. So we will get into modeling quadratics now because we've done exponential, we've done linear. And it's also about figuring out what kind of model to use when. So there are some rules. So we're gonna look at these graphs in class, but we're gonna move on. We're gonna look at these rules. So there's 3 different rules that we're going to have to know, and it's basically how do the numbers, line up. So the first rule is a sum rule. So basically, if you just add to get to the next number and all of your sums are the same, then it's linear. For example, so let me show you this as I go. So this first one, A, is a sum rule, because if you look, the difference, it's really a difference type thing, but anyway, we're adding to get to the next number. So 2 plus what equals 4? 2. 4 plus 2 equals 6. 6 plus 2 equals 8. And 8 plus 2 equals 10. So that's a sum on the left side. And they're all sums on the left side, at least for now. On the right side, we're looking at that difference. So 4 plus 5 equals 9. 9 plus 5 equals 14. 14 plus 5 equals 19. And 19 plus 5 equals 24. So this is why it's a sum rule. So this is linear, because on both sides, you're just adding a number to get to the next number. Then we have what's called a constant second difference rule. So the left side is still just plus 2. In this case, plus 2. Plus 2 is not always plus 2. Sometimes it's plus 1. It doesn't really matter as long as it's consistent. Here, not so much, right? 15 plus, actually minus 10 is 5. 5, let's see, that's plus 14. That's not 14. So that's 8, 5, 4, 3. So that's 38. And that's even bigger. Okay. Now, these are not the same. So we're going to look, because it's not growing super fast, we're going to look at a second difference. So let's find the next difference that we could use. I'm trying to, I was trying to change the color. I hope my screen's still working. So now let's find this difference. So that's plus 24. 14 plus 24 is 38. And then the next one would have also been a plus 24. I don't have a calculator right in front of me, but that's your constant second difference. So that makes this quadratic. And then when you would have to divide or multiply by something to get to the next one, that's going to be exponential. Exponential functions are a little bit easier to see with the data because those numbers grow really fast. So even if you don't do all of the math, though you should double check, but even if you don't do all of the math, these are still plus 2, plus 2, plus 2, and these are growing really fast. So that's how you know. Okay. Now this one doesn't have either of those rules, so it's actually not going to fall into any of these 3 categories. Fun fact, it's logarithmic. You probably don't know what that is, but all you have to know is that because it's not the same number as you add on the side here, on the left side, it should just be sum, so it's not going to fall into any of our categories. So you would have to use a calculator or just accept the fact that you don't know how to find that yet, and that's okay. The next thing we're going to do in example 2 is actually find a quadratic regression. And we're going to use graphing software. So in case you didn't know, we're going to get Desmos out. We're going to type this table into our graph. Now the first thing we want to do is figure out what model it should be. You can go with what we just learned. However, if you look at this side, they're not consistently the same added number, which doesn't mean we can't find it. It just means we're going to have to use something else. So let's look at what this data does on a graph. So let's see. So I've conveniently graphed it for you. Now that looks pretty linear. So let's come over here and we're looking at a linear regression. Okay, cool. I will say though that this section kind of lends itself towards being quadratic. So let's try to see what the quadratic regression would be. We're going to press the same button we did to find the exponential regression, but we're going to use quadratic, and hey look. these numbers are actually on a single quadratic regression line. A good indicator is this number right here. If this r squared value for a quadratic, when we try a quadratic, if that number is really close to 1 or in fact equal to 1, then the quadratic regression is the best result. If we look back at the linear, it's 0.9, our r value is 0.9993, which is very close to 1, but 1 is even closer to 1. So this is going to be the best outcome. So that means that this is our regression equation, and this data doing what it does is the reason why. So let's write down our linear regression. Our linear, not linear, sorry, this is quadratic. Let's write down our quadratic regression. And we're just copying it from what was on the graph. So we've got this plus 1.3x plus 4. Remember, your standard form for a quadratic function is y equals ax squared plus bx plus c. So you'll always see it in that format. Then it says use our regression to determine the vertical height of the ball above the ground when it's 100 feet away from home plate. Well, let's see. If it says it's 100 feet away from home plate and we're looking for a vertical height, let's look at what this data gives us. This is the vertical height. This is the horizontal distance from home plate. So this is the x and this is the y, which means that we're taking the number they give us and plugging it in for x. So we're finding y equal to negative 0.0032 times 100 squared plus 1.3 times 100, because we're plugging it in for both places where we had x previously. You take that, you're going to probably need a calculator, and when you type that into a calculator, you get 102. So it's 102 yards. Nope, I lied. What's the unit over here? Vertical distance above the ground in feet. So it's not yards. I don't know why I got yards. It's feet above the ground.